All right. So we started discussing a certain quantum information processing task last time. And I defined a quantity called the accessible information. So let's continue doing that and let's get to proving what is called the Holevo bound. I think with this result, I will not venture any further, or I just don't have the time to do any more quantum Shannon theory beyond this. So in proving this, I hope that I would have given, okay, there you go, somebody has joined us. Okay, so in proving this, I hope that I've given you some idea of um, what kind of techniques and tools are used in quantum Shannon theory, right? And if either in today's class, if we have time, or in tomorrow's lecture, I'll just try to give an overview of a few more results of quantum Shannon theory or quantum information theory, which we will not have the time to really prove. I mean, even Holevo, I can simply state it and move on, but that'll just be like, I'll be doing bullet points, but I don't want to do that. So I want to try and prove Holevo bound today, and tomorrow just give you an overview of what else, what more beyond this. And somebody wanted me to give a wrap up of the course to say what all have we done in this course really, because it might have been a bit of a random walk, classical or quantum. But the idea was not to have a random walk. So maybe we'll discuss overall what we have done. And maybe I'll take some feedback from you guys also about this course itself. This is the second time this course has run, this advanced topics course. We're still working on the content, right? Like the basic QCQI, it's very clear what has to be done and, yeah, at least what can be done. But this one, I'll get some feedback from you guys on, what you felt about it, okay? All right, so what is the task at hand? It is to communicate. So the task that one is discussing is that of transmitting classical information using quantum states. And so obviously, this will be over a quantum channel, right? But to begin with, I'm going to assume that there is really no noise in the channel, that this is somehow some ideal transmission that is happening from sender to receiver. So the kind of picture that we have is this, that you have a sender who has a classical source with her. And this classical source is generating some symbols. So associated with this is a classical random variable, and there's some set of symbols x which are generated with probability px, and this x could go from some 1 to n or 0 to n minus 1. And then A is going to encode each of these symbols into a quantum state. So while the source is generating a classical random variable, A is going to generate a quantum ensemble corresponding to this classical source. So she is going to prepare a bunch of quantum states rho x with probabilities px. And this is going to be transmitted over her quantum channel, which we assume now is like an identity channel effectively. It is no noise, right? And this again, x goes from 0 to n minus 1. This goes to B. B receives this information, and now B has to decode it in order to extract back this classical information which A has encoded. How is B going to do the decoding? B is going to perform a quantum measurement, right, of the received states. And the most general kind of measurement that B can perform is obviously a POVM. So let's say that this is a POVM with elements EY, and let's say Y goes from some 0 to m minus 1. M need not be the same as n in general, right? And then depending on which outcome E gets, or basically the what B generates by doing this POVM measurement is to generate another classical random variable, except that this is a classical random variable y, right? Where there is now a certain, so I can of course talk about the probability of getting the index y, a particular index at the end of this measurement. But more pertinently, I have to talk about the conditional probability of getting y given x, right? I have to talk about the probability of y given x, because when state rho x is sent, what is the probability that B is going to decode that? So essentially, this is the probability that x was sent, but is going to be decoded as y, right? So this, what is this going to be? State rho x is sent, but the measurement outcome is y. Place rho x ey, exactly. Okay, so I hope everyone remembers this. So this will be the quantity of interest here, the classical quantity of interest, right? It's going to be the conditional probability of getting y given x, right? Okay, so this is the setting that we have. Sorry about this. All right, you can still see this, right? Fine. So now, how do I quantify how well I have performed this task, or how well have the sender and receiver performed this task? And this is what we were discussing last time, that you have to compare two classical distributions now. You have to compare the source distribution Px and the eventual distribution Py. You have to compare Px and Py, but what you have is actually the conditional distribution y given x. Okay, so I hope that is clear. So now the way they're going to do this is by using a mutual information, a classical mutual information. So the quantity of interest here is what is called accessible information. So the accessible information is essentially associated with a particular ensemble. So the accessible information of this ensemble of states, Px rho x, is basically the maximum classical mutual information Ixy between x and y, maximized over what? Maximized over all possible POVMs that can be performed by the receiver. Right? So for a given ensemble, we would like to know, so essentially what the accessible information is capturing is what the word says. It's how much information capacity does a certain ensemble of quantum states have? Or in other words, if information is encoded into such an ensemble of states, how much of that information is accessible? How much classical information is accessible from a given ensemble of quantum states? So one can think of this as the information capacity of this ensemble of states. And of course, keep in mind that this is the classical information capacity, right? Because you're finally encoding classical information in quantum states here. Okay. Right. So I think I discussed this briefly last time also. So what is a general upper bound on this quantity? So the question that the Holevo bound addresses is how large can this accessible information be, right? What is the maximum accessible information for a given ensemble of quantum states? So if I look at this quantity here, which is the classical mutual information, you know that the classical mutual information is bounded by the Shannon entropy of the random variable x, right? If you recall this sort of diagram that we had, x, y, you know that the mutual information is sitting somewhere here. The maximum that this mutual information can be is as large as hx itself, right? And this happens when you can perfectly decode whatever has been sent, and this is indeed the case classically, right? So unless you have a noisy channel, which we've not introduced a noisy communication channel yet, if you simply assume that there's a classical source generating symbols according to some distribution and being sent over to B. Classically, this can be perfectly decoded. There's nothing that prevents the receiver from being able to saturate this inequality. So this inequality is part of what is called the classical data processing inequality. Again, one of the many things that I haven't had time to really talk about, but there's a small section in Nielsen Chuang chapter 11 that you can look up if you're interested, right? So classically, this can be achieved because all symbols are perfectly distinguishable. Right? So this is the maximum that this can be, even if I use quantum states finally, right? But now the question is, what is an upper bound on this as far as quantum states are concerned, right? And that is the question that is answered by the Holevo bound. It says that quantumly, this quantity, which is maximum over all POVMs of this classical mutual information between the sender and the receiver, this is upper bounded by this quantity, which is S of rho minus sum over x px S of rho x, right? So for a given ensemble, this is what is called the Holevo bound. This quantity on the right turns out to be an important quantity to associate with a given quantum ensemble because, like I said, it is capturing the information carrying ability of that ensemble. So this is given a name in itself. It's often called the Holevo chi quantity associated with an ensemble. Okay. This is S of rho minus. So how do we see this? How do we see that this capacity is nothing but the concavity gap or the Jensen gap of the ensemble, right? That's what this is saying. So why is this true, and how can you even show something like this which holds for any POVM, etc.? So that's why I just want to do the steps involved in the proof of this thing. So let's try to go over this. So let's try to prove the Holevo bound. So notice that we will start. So this is what I was doing last time. So we start with a tripartite state of three quantum systems. P, Q, and M is what I think I called them. The idea is that, okay, so let me write down the state and then you will see what each of these parts stand for. This is, of course, in general a density operator because you're encoding in an ensemble of density matrices, right? Px rho x. So this is of the form sum over x px. First, there's a classical register x. This is what is called P. And then there is a rho x, which is what I call Q. And then there is the measurement register, which is initially set to 0. So these are the three systems in play. This is a, you can think of this as a preparation system. This is basically like the sender has at her disposal some classical index, right, associated with what the source is sending her. So she is going to read off the index x and based on that pick the state rho x. And since the classical index is sampled according to the distribution px, so also the rho x is going to be sampled according to the same distribution, right? So this classical register that A has is what we are calling P essentially, right? we are associating a Hilbert space with that. We're associating a set of orthonormal states in that Hilbert space, which is the set ket X, right? So effectively, this is the system P here, which represents this, right? And finally, this is the system M, right, which is representing this measurement device, right? And in between, what we have out here is the state rho X, which at any given point is either sitting in A's lab or in B's lab, depending on whether it has been sent to B or not, right? So that is the system Q, right? So these are the three systems in play. Yeah. So this ket X is an orthonormal basis in the Hilbert space that you associate with the preparation system. You can variously think of this as a classical register or a reference system, etc. Right? Okay. So this is where we start initially, and then finally what happens? The state rho has been sent across. Notice that there is no noise channel anywhere in the picture. Suppose the communication channel was noisy, then I would first have to transform this rho X according to the quantum channel N, which I'm not going to do now, right? Instead, I assume that the rho X is transmitted to B as is, and then the only transformation that happens is the measurement that B is doing. So now we have to write down what happens to Q and M after the measurement, right? Nothing happens to P because P is simply a classical register that's sitting with A, right? Nothing has happened to P. So notice now that initially what is happening is P and Q are coupled. To be precise, they are entangled, correct? Systems P and Q are entangled to begin with. They are correlated because rho X is picked depending on what the symbol X is. So these two are entangled to begin with, but M is just uncoupled at this point, right? So when I say final, I simply mean that a transformation has happened such that now M is going to get entangled with P and Q, correct? So let's write down the final state. So I'm going to call this rho P prime, Q prime, M prime, and P prime is going to be the same as P in the sense that no change has happened, but Q and M are going to undergo a change. So let's first recall what the measurement transformation looks like, right? Yeah, so I think it's nicer to draw a figure and understand this. So, so if they were just, okay, so there are two figures that I will draw. So first, let me say that I have this measurement device M, which becomes M prime or whatever after the transformation. Okay, let me not call this M, that's going to confuse things. So let me say that this is the box that is going to implement the POVM EY. I have some state rho X which is coming in, right? Now, what is the output going to be? What is the, if outcome Y was obtained, what is the post measurement state? It's not just EY, rho X, EY. The POVM elements are EY. So the transformation that you associate with this involves the square root of these things, right? Because recall that these EYs are all positive, semi-definite, and they sum to identity, right? So the transformation that you associate with this is of the form square root EY rho X square root EY, right? Because you need something which is a valid density operator at the end, right? How do I get a valid density operator at the end? This is the state that is associated with a given rho X. This is not normalized. So I will normalize it by putting a trace square root EY rho X square root EY. And then I will say that the complete transformation, so the full post measurement state for a given rho X is going to be sum over all of this, right? I will weight it by the probability. So note that whatever I used for the normalization is nothing but the probability of getting outcome y given rho x. So yeah, so maybe I should add somewhere. So notice that the probability of outcome y given rho x, this is what I wrote down earlier as a conditional probability. This is trace rho x ey, right? That's what you told me, which is the same as trace square root ey rho x square root ey, right? So it's simply the norm of the, or the trace of the final density matrix after the transformation associated with a particular outcome y, right? So I hope you see that this is what it is, and this is what we called also the conditional distribution py given x, right? So the full state is going to be this probability times this. So let me just write down. So it's simply going to be this. Right? So for a given x, the state is going to transform as sum over y square root ey rho x square root ey, because I multiplied and divide by this. I multiply by the probability and I divide by this normalization. They turn out to be the same, right? So this is the post-measurement state for a given rho x. Now you understand that this transformation I am modeling using a third system, right? Now when I'm writing down this POVM transformation, there's only a single quantum system in play. Correct? This box is some transformation that is being done on this quantum state. So it's like a map that's being done on this quantum state. So, but the action is all happening in one system. Now I'm saying that I'm coupling another system with this. So effectively what I'm doing in some sense is I'm giving you a model for implementing the quantum measurement. I'm sure this is a question that many of you asked or had last semester when we were discussing things like POVM. This is just an abstract box, right? This is just like, I'm not really telling you what is happening out here. But one way that this transformation can be realized is as follows. That's the sort of physical part of coupling this second system. So this POVM transformation can be realized as so I have this Q, right? System Q. So now I'm actually drawing two different systems, okay? And there is an M. So this is the system of interest and this is the measurement device. This is in state rho x initially. The measurement device is in state ket 0 and initially they are in a tensor product state, right? So this is like, I'm saying that there is a Hilbert space HQ here. There's a Hilbert space HM, which represents the measurement device. The measurement device, for all practical purposes, is only going to manifest via some classical, like a dial. So it starts in 0. Eventually, it's going to be one of the y's. That's what it's going to show me. So post measurement, right? This is going to be in some state. Let's say it's in the state square root ey rho x square root ey, which means that outcome y is realized. Then associated with that, the measurement device is going to be in the state. So initially they were uncoupled. So this is initial. They're unentangled. But finally, they get entangled. So in a sense, what we are saying is that this collapse that is happening as far as the system alone is concerned is happening because you looked at the measurement device. And when you look at the measurement device, you're collapsing the measurement device to one of these ket y's. And depending on which ket y you saw in the measurement device, you're saying that the state itself has now collapsed to that particular outcome, that particular post-measurement state, right? So this transformation, which is rho x q and 0, 0 in M, going to sum over y, post measurement state associated with each y. This is again q. right? So this transformation, I'm now going to claim, is a CPTP map. So I'm realizing the system POVM by coupling a measurement device and by a transformation or a map which is acting jointly on Q and M as a CPTP map, right? As a quantum operation, what we studied in the very beginning of the course, right? So this is a general quantum operation on this joint Hilbert space Q and M, right? And what are the Krauss operators of this quantum operation, or what are the Krauss operators of the CPTP map? So notice that what is happening to the measurement device is basically it's starting at 0, and then the y index we said goes from 0 to m minus 1. So it can either go from 0 to 1 or 0 to 2, or it can remain in 0, or it can go from 0 to something, m minus 2, whatever it is. So this is just a permutation of the basis, right? Because I've picked some basis. So sometimes this is called a pointer basis, right? People who work on measurement models and all that. Sometimes this is called a pointer basis because it's just one of a set of orthonormal states, and your dial is going to point to one of those things depending by some throw of dice or something, whatever, in whichever way that this is realized. But mathematically, it's just a permutation of the basis, right? Which is what kind of transformation? It's a unitary map. It's a unitary transformation. So I can devise, so I can basically think of, so let me say that this, okay, so let me call this some map E, okay, which is taking this to this. So now I'm going to write it like this, okay, EY tensor UY acting on rho x tensor 0, 0. And on the other side, I again have EY tensor UY dagger, okay, where UY acts on 0 to give me 0 plus Y mod M. It's precisely this shift kind of operator, which we've seen last semester in different algorithms, particularly I think when we were doing phase estimation, right? After we did the Fourier transform and then you did phase estimation. So when you do phase estimation, you do encounter these kind of shift operations or operations which just permute the basis, right? So on the M system, there is a unitary transformation. On the Q system, there is a transformation by some arbitrary positive operator, square root of EY. And together, they constitute like a Krauss representation. So the Krauss operators of E are square root EY as far as the Q system is concerned, and a unitary UY as far as the M system is concerned. Okay. The fact that the map is completely positive already comes from the fact that I have written out a Krauss representation explicitly. I have written out an operator sum decomposition for this. But is it trace preserving? That is something you will have to check and tell me, hopefully in the tutorial. Okay. So I will leave it to you to check that CP is easily done, but TP also, you will have to check that. Okay. So in a way, I like this proof because it ties in things which we have done earlier, right? It helps you understand how you can do a POVM as a quantum operation on a larger system, including a measurement apparatus. And it also helps you see how you can have CPTP maps on coupled systems like Q and M. And initially Q and M were unentangled, but after the action of the CPTP map, they have become entangled via this whatever this measurement transformation was, right? Okay, so this is how we are modeling this process of decoding by the receiver via this additional measurement system. And yeah, this is just one way to think about how the transformation can happen. Okay, so going back to where were we? So we were here at what is the final state, right? I still haven't written down this state. So what is this final state? What I want to write down. So now that I have hopefully convinced you that this is what the measurement transformation looks like, now we can write down the final state, the final tripartite state, as rho p prime q prime m prime is a sum over x and a sum over y, right? So sum over x, px, xx, that is still p or p prime, doesn't matter. And then I have here a square root ey rho x square root ey y. So this is q prime, this is m prime. So it depends on, some people like to put the prime on the state. You can put it for the systems. Yeah, it's a it's a question of how you view it. But yeah, I'm just following the notation in Nielsen shown. Okay, so this is the final state. Now, what is Holevo bound telling us? Okay, so or having written down these states, how does one prove the Holevo result? So now the steps of the proof. So let us write down the quantities on the left hand side and the right hand side. Right? So first is for a given POVM, Ey, what is this quantity, the classical mutual information between X and Y, right? How do I actually quantify this? So the classical mutual information, if you recall the definition, is simply the Shannon entropy of X plus the Shannon entropy of Y minus the joint entropy. So I'm going to claim that for a given POVM, this mutual information is nothing but the quantum mutual information. So I don't think I used a different symbol for this, although the book does, but I stuck to the symbol I for the quantum as well. So the quantum mutual information between what and what, between the preparation system and the measurement device, right? In the final state. So that's why I'm putting the primes here. Obviously, the preparation and the measurement are coupled only in the last step, right? After the measurement. So the claim is that these two things are the same, right? So let's write down. So I've written out for you what the left-hand side is. So let me call this as 1. Okay. So I'm going to prove 1 now. So I've written out for you what the left-hand side is. So what is the right-hand side? To write down the right-hand side, I need to know the marginal state, right? I have to go from the tripartite state to the bipartite state. So this is rho p prime n prime, where I have to trace out just this middle part here, right? So what is this now? This is just sum over x and y, px followed by trace of, so I hope you see that square root ey becomes a single ey in the trace, right? So it's just trace rho x ey, x and y. So effectively, these are two classical systems, right? This is the p prime and this is the n prime, which are coupled according to this joint distribution. But note that this trace rho x ey is nothing but the conditional probability of getting y given x. So this is nothing but sum over xy px py given x. So I hope you can see that. So what is this? What is px times py given x? No. That's a joint distribution, right, between x and y. What do you call this? Classical probability. This is some form of Bayes rule, right? Yes. What is a joint distribution between x and y? It is px times py given x. If x and y are independent, then py given x is the same as p of y. So P of xy becomes just Px times Py, right? So this is nothing but the joint distribution Px comma y. So you can sort of directly read off from here that this quantum mutual information is going to be the same as this classical. But anyway, we can still do a couple of steps here. So we can say, so yeah, let's define now so let's define the quantum mutual information here between P prime and M prime in the state rho. This is now the von Neumann entropy of the P prime system, the von Neumann entropy of M prime minus the joint, right? So what is S of P prime? To get that, you have to trace out the M system, right? And when you trace that out, what are you left with? You're left with Px xx, right? So you see that this is nothing but you essentially get the same thing, right? H of x plus h of y minus h of xy, right? Which is nothing but ixy. Okay? You see that? So okay, so if I take the final state and I trace out the Q system, which I should, because the classical information is only residing in the M, the measurement apparatus, right? And I have to compare that with P. Then you see that the quantum mutual information between P prime and M prime is the same as the classical mutual information. And that's the classical mutual information associated with a particular QOVM. And that's what is on the left-hand side of the Holevo result. So what's on the right-hand side? So the second step, or I don't know, I think I may have reversed the order, but it doesn't matter. But what you can notice is that the yeah, so this is done, the final state, the initial, yeah, okay. So you note that what's on the left-hand side of the Holevo result is nothing but the mutual information, the quantum mutual information of the final state, right? So now I want to write down what is the quantum mutual information of the initial state, right? So where did we start with? What is the initial quantum mutual information? And this is now obviously the information is only between P and Q. M is uncoupled to P and Q. So this is the mutual information between P and Q in the state rho, right? Remember that the state rho PQ without the M system is simply this. So can you work out what is the mutual information in this state? So I'll give you the definition. It is the sum of the von Neumann entropies of the individual subsystems minus the von Neumann entropy of the joint state. So this is S of, I want to write it like this, S of rho P plus S of rho Q minus S of rho PQ. So can you evaluate this for me? So this is P, this is Q. So you have to get the marginals, right? Then tell me what is the von Neumann entropy of P, Q, and from that subtract the von Neumann entropy of the bipartite joint state. So I'll give you a couple of minutes. Yes, what is first term? Correct. Good. Yeah, the Farnham entropy of the P subsystem, because once you trace out Q, you're simply left with sum over X, Px, Xx, right? And X is an orthonormal basis, so the diagonal in, writing down a diagonal state, so weighted by the P. So that should be just be the Shannon entropy of Px. What happens when you trace out P? What is S of rho Q? So you're saying it's S of rho itself, right? It's meaning it's S of sum over X, Px, rho X. Correct. Good. So this is S of rho itself. Remember, rho is sum over X, Px, rho X. Okay. So what's the, now this joint entropy, the joint Farnham entropy of this bipartite state, we've computed this a few times already in the past few weeks. We have a bipartite system where on one subsystem, the states are all orthogonal. Right? So if I view the bipartite system, right? Plus, yes, correct. Yeah. So this is, we've seen this before. You can view this as having two sources of information or uncertainty. There is the part that comes from the Shannon entropy of the Px plus the weighted sum of the quantum entropies of the individual density matrices, right? So you see that these two classical bits cancel out. And so what you have is S of rho minus sum over X Px, S of rho X. So what is this? This is the quantum mutual information between P and Q initially, right? So this is what we have shown. Okay. I think I called that first equation as 1 and the second equation as 2. So if you notice, now if you recall what the Holevo bound looks like, it says that this classical mutual information between X and Y, of course, okay, maximized over all of these EY, is less than or equal to this. In other words, what that is saying is, so that's what we have just shown, right? We have shown between 1 and 2, what we have shown is that this Holevo bound statement, proving this Holevo bound would be the same as proving that the final quantum mutual information between P prime and N prime, again you can say max over all EY, is less than or equal to the initial quantum information, mutual information between P and Q, also in the state rho, right? So this is what the Holevo bound is saying. It's saying that the initial, and again makes intuitive sense, right? You cannot finally hope to have any more quantum correlation between your preparation and the measurement system than you had initially between the classical index P and the quantum encoding of that, which is Q, right? So this is what we have reduced the Holevo result to. So remember now these three systems P, Q, and M. This is the classical index X. This is the corresponding quantum encoding. And this is the final measurement So it's saying that you cannot have any more correlation between P and M than what you initially had between P and Q. That this is an upper bound for how much quantum mutual information you can have between P and M. And that quantum mutual information between P and M is exactly the classical mutual information between X and Y. That's what we have shown so far, right? So now all that remains for us to do is to actually make this statement concrete, is to actually prove this, that the final quantum mutual information cannot be any greater than the initial quantum mutual information. It's a little bit, I mean, it's not as straightforward as saying that mutual information does not increase under quantum operations. For example, I can make that statement, right? If I prove, for example, the statement that mutual information cannot increase under a joint quantum operation on two systems, that still doesn't fully prove this, because the systems have gotten swapped somehow, right? There's P and Q here, and there is P prime and M prime here. So the way to now show this statement, so let me call this as 3, is to break it down into two parts again and prove it. So clear so far? I mean, I can stop here, but I just want to take this to completion. So let's try to prove this statement 3. Okay? All right. So now the aim is to prove 3. So notice that we started with, so instead of looking at just PQ, let me look at the initial part. Let me look at the mutual information between P and QM. Okay, because I want to bring M into the mix. But initially, remember that while PQ were entangled, M was in a tensor product. M was in a product state with respect to P and Q. So just based on this, I'm going to say that whatever quantum correlation there was between P and Q is the same as the quantum correlation between P and QM. So whether I put the M there or not, it doesn't matter, because M is in a product state and M is in a fixed pure state, and it's in a product state with respect to P and Q. So is this first step clear? Right? So the reason is because M is initially, so we start with this. So note this, and this is because M is initially uncoupled to PQ. Okay. So now, yeah. Mm-hmm. So let's check that. Okay, so that's a good point. So let's check that. So does it hold for any product state, or is it that it has to be only a fixed pure state? So what is this mutual information? Again, let's go back to the definition. So this is S of, let's say, rho P plus S of rho QM minus S of rho PQM, right? So now what will this be? S of rho P plus, now S of rho QM is going to factor as something rho Q tensor something in rho M, correct? And you know that so I can factor this as rho Q tensor rho M, and the entropy of the tensor product, the von Neumann entropy of the tensor product is sum. Do you see what's happening? You do the same thing with this tripartite entropy now. Again, I'm going to split it as PQ tensor rho M, correct? Because PQ is in a tensor product state with M. Once again, this splits up, then, so you see, it doesn't matter what the state is. So long as it's a product state, so I can add any number of, I can attach, so if I have this joint system PQ, I can attach any number of M systems, M1, M2, M3, doesn't matter. So long as they're all in a product state vis-a-vis the PQ, they don't add anything to the mutual information between P and Q. Doesn't matter if they're pure or mixed. Right? Okay. So good. So we proved the statement also. So this is nothing but then the mutual information between P and Q. Right? So this is the first step. So we've made it into a tripartite. We've brought in the M system also. Now we can do the quantum transformation, right? So I'm starting now with the right-hand side of the Holevo, right? That's where I started. So this is the RHS. Okay. So I write it like this. So RHS is this, the same as this. And now so this is all initial. Okay. And now the final quantum mutual information. So QMI is quantum mutual information is P prime, Q prime, N prime, right? So now I'm going to use two results from the previous chapter, which I did not prove then, but we can now again prove these things in the next 10 minutes. It's essentially a tutorial for you guys. So you can prove these two results with me. So we are now going to use two statements. So we're going to invoke two, let's say, properties of the quantum mutual information. So the first, I don't know, calling various things 1, 2. Okay. So A, we'll note that the QMI, which is quantum mutual information, does not increase under a quantum operation. What that means is, of course, here there are three systems in play, but even if I had just two, the point is if rho P prime, Q prime, M prime is the result of some quantum operation on rho PQM, right? Then this quantity, so actually one has to be, well, doesn't matter here, but the quantum operation here is of a particular kind, right? It is happening, so its identity as far as the P prime system is concerned, and there is a measurement transformation, which is what we modeled as this CPTP map E acting on Q prime and M prime, right? Okay, so this is the nature of this quantum operation. It's identity on P, and there is something non-trivial happening on Q and M. Then the final mutual information after the transformation always has to be smaller than the mutual information before the transformation happened. Right, so this is final, this is the initial. Okay, so this is the first property, that quantum mutual information does not increase under quantum operations. What is the second property that we will need? So how do we go from here to what you actually have on the left-hand side of Holevo? You have to trace out one of the systems. Which is the system you trace out? Q. You have to trace out the Q prime, right? So the second property is that discarding systems does not increase mutual information. And therefore, the mutual information between P prime and Q prime is always less than equal to the mutual information between P prime and Q prime M prime. When is it equal? When is it equal? That's the case we just saw, right? Yeah, when M is just a tensor product with P. But notice that this final state is not like that, right? The final state is something where there is non-trivial correlation between the Q prime and the N prime, and you're discarding that. So then obviously the amount of mutual information you can share jointly with Q prime and M prime will be greater than the amount of mutual information you can share with just M prime, right? So discarding a system cannot increase the mutual information. It can only decrease the quantum mutual information. Okay. Yeah. Yeah, we're going to show both of them right now. Okay. That's the next 10 minutes. Hopefully we'll complete this today. Okay. Okay. So it turns out that to show both of these things, I have to invoke a certain property of tripartite. So now we're all, I mean, these are all like tripartite systems, right? I have a tripartite system. I'm discarding one system and I'm saying that the mutual information does not increase. Then I'm doing a quantum operation on a tripartite system and I'm saying that the mutual information does not increase. So there's a fundamental property of tripartite quantum states. For bipartite states, we proved something called the subadditivity. So for tripartite states, there's something called the strong subadditivity. Okay, so that's what I'm going to talk about next. I remember at the previous edition of the course, I didn't do it in this sequence. I first did the strong subadditivity statement while I was proving various properties of quantum and entropy. And by that time, I think students were wondering, why am I proving yet another property of this quantum entropy? I mean, yeah, I mean, you can keep adding systems and you can keep writing down these inequalities, but it turns out that this is where it comes in, right? So finally, to prove any statement in quantum information processing, you have to go back to all of these properties of the entropy. Okay. So yeah, hopefully I have now motivated you enough to stare at the subadditivity statement. So let me write that first. And then we'll prove B first and then we'll prove A because it turns out that they are sort of related in that sequence. Okay. But okay, let me just complete this now. So I hope you see that once we prove A and B, let's say you assume that I proved A and B, then you see that this final, I mean, not P prime, Q prime, M prime, but actually then, so given A and B, once I put that together, then I have this final mutual information between P prime and Q prime is always less than or equal to the initial mutual information between, here should be N prime, right? Because I was tracing out the, made this mistake last time. I was tracing out the Q prime, right? So what I should have here is M prime actually. So this is what I want to show. Correct. And this is true for any POBM that the receiver can do. And so this becomes an upper bound for all POVMs that the receiver can do. And so this implies essentially the Holevo bound. Okay. So I hope you see this is done, right? But now we need to go back and show these two properties of the quantum mutual information for tripartite states. So let's do that for the next 10 minutes. So the Holevo result is done, all right? But we're just going to prove these two properties of the QMI. We need to know a certain property of the von Neumann entropy for tripartite states, and this is the so-called strong subadditivity. It's called SSA. Today, this has become such an important property as far as understanding quantum states is concerned that people across physics, including condensed matter theorists and cosmologists, I'm saying this from physicist perspective, all of them are trying to learn and understand what the strong subadditivity is. Okay, because this has many manifestations, can be viewed in very many interesting ways and so on. That's a whole project in itself. But let me just write down what it is. So recall just what basic subadditivity was. You were comparing SA plus SB and SAB, right? Or if I had a bipartite system, then you're comparing the sum of the subsystem entropies and the joint entropy of that bipartite state. And which way does the inequality go? So subadditivity of the von Neumann entropy. Okay, correct? Fine. So, I mean, one easy way to immediately think about this is if I take this side with a minus sign, what's the quantity on the left? One way is relative entropy, the other is its mutual information. Yeah. So both of which are positive. Okay. So strong subadditivity tells us something about it's a similar kind of inequality where you're taking marginals of a tripartite state and you're trying to understand how the sum of the subsystem entropies relates to the joint entropy. And there are two equivalent ways of writing this, and I will write down both. Okay. So one way so you have a tripartite quantum state. And of course, it could be correlated in very many ways. It could be correlated across just the A cut. So A could be correlated with B and C, but B could be in a product state with respect to C, or it could be correlated across every cut, which means there is entanglement across AB, BC, and AC. Or it could be a product state, AB, some rho A tensor, rho B tensor, rho C, etc. So what the strong subadditivity tells you is how these different entropies are constrained in a tripartite state, right? So, for example, what the basic subadditivity tells you is how these are constrained, right? And it tells you, for example, that I can have a bipartite pure state which has zero entropy, whereas the marginals have maximum entropy, right? And it also tells me that if there is no entanglement in the state, then the sum of the subsystem entropies is equal to the sum of the joint entropy, right? Fine. So let's look at this now. So this says something about S rho ABC plus S rho B is less than equal to S rho AB plus S rho BC. Okay. And this holds, you can sort of permute things around and this will hold, this inequality will hold. So I'm not at all going to get into even attempting to prove this, okay? But I will tell you what this means by rewriting it in a slightly different way, and even showing this equality is a non-trivial task, okay? So I'll at least put this in the tutorial. So in the tutorial, you will show that this statement also means this statement, which is S rho A plus S rho B is less than equal to S rho AC plus S rho BC. Okay. So this kind of a statement, what I've written down in the second line, right, is a somewhat trivial statement if you think about this for classical entropies. Okay. Why is it a trivial statement? Because in the classical case, of course, you still have subadditivity. Okay. But the individual entropies cannot be larger than the joint entropy. Remember again these sort of Venn diagrams that you could draw, where this was the individual entropy of, let's say, the classical variable x, this was the individual entropy of y. You could never have a scenario where h of x is actually greater than this sum h of xy, or the joint entropy h of xy. But quantumly, you know that it's very much possible, not just is the sum larger than the joint, which is true classically also, right? That this plus this is greater than this, and it's greater by exactly this amount, which is the amount of correlation that you have. But quantumly, you can have the individual SA being greater than S of AB, SB being greater than S of AB. But what this is saying is now if I have a tripartite system, the sum SA plus SB is still constrained by the joint entropies AC and the joint entropy BC, right? So what this is saying is I can, for example, have S rho A being greater than or equal to S rho AC, right? So quantumly, this is possible. And S rho B can be greater than or equal to S rho BC, but the sum, right, cannot be larger than the sum of this. Do you understand? So what it means is, okay, this, for example, would be a signature that there is some entanglement across AC. This would be a signature that there is some entanglement across BC, right? So now think of this tripartite situation. I have A, B, C, okay? They can all be entangled with each other, right? So while A can have a certain amount of entanglement with C, B can have a certain amount of entanglement with C, but C can only have the amount of entanglement that C can have with A and the amount of entanglement that it can have with B is globally constrained. And this constraint actually is what is often called monogamy of entanglement. You see, what this means is that SA, for example, cannot be arbitrarily large, like in the bipartite case, where SA could be log D and SAB can be 0. SB can be log D and SAB can be 0. But in this case, for example, you cannot have a scenario where S rho AC is 0 and SA is log B. Because if you had such a scenario, then it will mean that something has to happen for B and BC. So if you flip it around, then what is happening? I have a single subsystem C, which is entangled with both A and B. And this difference, in some sense, quantifies how entangled C is with A. You can think about this difference as quantifying how entangled C is with B. But the sum of those differences is constrained in a particular way. So C, for example, cannot be maximally entangled with both A and B. If C is entangled with A in some non-zero way, then the amount of entanglement it has with B is constrained. So what this says is, while these individual subsystem entropies can be larger than these bipartite entropies, because they're sharing it with a common system C, right? C has to be monogamous finally. It cannot have maximum entanglement with both A and B. The amount of entanglement it has with A is constrained by how entangled it is with B. Okay? So this is one manifestation of what is often called the monogamy of quantum entanglement. This is one way of understanding what this messy inequality is saying. Okay? Questions? Okay, so how does this now help us to prove those properties? I think Sriram is like, why did I ask? Sriram, right? Sorry. Yeah. You were the one who wanted to know how A is proved. So you can imagine the route that people are taking to this, right? I mean, the strong subadditivity itself is an extremely non-trivial statement to prove. And if you now Google up the literature, you will find that people are rewriting proofs of strong subadditivity all the way up to something like 5 years ago, because it turns out to be a very deep property in what is called functional analysis, where you try to understand the structure of these density matrices for example, does this hold for infinite dimensional Hilbert spaces? Does this hold only for finite dimensional Hilbert spaces? Does this hold for field theories? So people are looking at this in various ways. So this is a highly non-trivial thing to prove. But anyway, let's assume now that we have the subadditivity. Then it becomes very simple to prove, for example, that discarding systems does not increase the quantum mutual information. So let me just prove that statement, and maybe I'll stop today and we'll come back to the first statement tomorrow. So let's now get back to B, which is that discarding systems cannot increase. It's just a very simple consequence of subadditivity. Okay, so let me write it in a different form so that it matches with the way I've written down the subadditivity here. So what you want to say is that if I have a tripartite system rho ABC, and let's say I trace out C, so I end up with rho AB, right? Then I want to say that this tripartite mutual information between A and BC will have to be greater than or equal to the mutual information between AB, right? That's what we're trying to say. So let's try to write down these quantities. So what's on the right hand side? you know that that is just this. Okay. And the left hand side is S rho A plus S rho BC minus the joint. So now just invoke SSA. What does SSA tell you? It tells you that, or let me just take the difference between the, so let me do this. No. Okay, let me take the left hand side and work my way through this via subadditivity. So what do I have in subadditivity? I have, so it's basically like I flipped the sign around, right? Okay, I have A plus BC. So yeah. So I can either use this form, but I would, so let me just replace the tripartite mutual information from the subadditivity inequality, right? Does the sign work out in the right way then? Yeah. So SSA tells me that, let me write it down. So it tells me that rho ABC plus rho B is less than equal to rho AB plus rho BC, right? Yeah. So let me, so this tells me that the left hand side then has to be greater than or equal to S rho A plus S rho BC. So I'm just substituting this here, right? Minus S rho B minus this. Okay. So why is it giving me a wrong sign? This comes with a plus, correct? So this cancels out. That's it. So it gives me yes. Okay. I've just used subadditivity, strong subadditivity. I've substituted from strong subadditivity for the tripartite, like this. So yeah, once you have this kind of an inequality, you can prove various statements like this. So one of them, what you've just shown is that if I have this tripartite mutual information and I discard one of these systems, so I can do this in, I can permute things around and do it the other way around also, because like I said, you can change these indices here. So if I put A here, I have to make sure that I symmetrically replace B with A, right? And then C with B and so on. So if I do that in the right order, then I can show this for various systems. So this is done. Going back to A, which is to show actually that quantum mutual information cannot increase under a quantum operation, requires a few more steps, of which subadditivity will be one. So let's do that tomorrow. Okay, it's probably the last proof that I will do. Yeah, so you also notice that I didn't tell you about when is subadditivity saturated with equality. So it turns out again that that's not a very easy statement to make. For regular subadditivity, the answer was clear that this is equal if and only if AB factors into the products of its marginals, right? But this tripartite case, it turns out that equality holds if and only if, the way I've written it, which is with ABC like this, it holds if and only if this tripartite state rho ABC forms what is called a quantum Markov chain. Okay, and it should form the quantum Markov chain in a particular sequence, which is ABC. I mean, this is all extra. I'm not even going to venture into any of this for your end sem or something, but just for those of you who would like to know this, what it means to say that ABC form a quantum Markov chain, or that rho ABC is in a state which is a quantum Markov chain. The idea is similar to what a classical Markov chain is. So do people know what a classical Markov chain ABC is? Yes, what is it? Yes, so what is it? Okay, but what does the Markovianity property mean? When I say that I have three random variables A, B, C that form a Markov chain in some sequence. Yeah, so the next, okay, so I put a sequence. So what it means, for example, is that C is independent of A given B. So I have three random variables A, B, C, which could be correlated in any which way. But if I say that they form a Markov chain in this particular sequence A, B, C, it means that while B depends on A, C depends only on B, and it depends on A only via B, because B depends on A. Or in other words, B is correlated with A, C is correlated with A only through B, or in other words, it is conditionally independent of A. Because once you're given B, all the A dependence has come there. So it's conditionally independent of A given B. So in a similar way, what it means, if the subadditivity, strong subadditivity is saturated with equality, it means that this tripartite quantum state, let me just write this very here, it factors in a very interesting way. It factors such that it's always correlated in the AB sector. It is correlated in the BC sector, but it's as if the system B is split down the middle, and people often write this as a B left and a B right. Okay. So it's as if the system B is split down the middle, like exactly how a classical Markov chain would be, so that C is only correlated with A via B, and C is independent of A given B. Okay, so that's what a quantum Markov chain means. I'm writing a very simplistic structure. There is more to it. There is like a subspace and a subsystem structure and all that, but just want to point this out, that in case you were wondering what the equality condition for strong subadditivity is, it is saying that this, so if I again try to draw diagrams for this, then there is a part of B that is correlated with C. There is a part of B that is correlated with A, but somehow C is conditionally independent of A, and it's correlated to A only via B. So there are parts of B which are correlated with A, there are parts of B which are correlated with C. Together they form an entangled state, but when the inequality is saturated, the B system factors in a nice way between A and C. That's what it means. It's a very cartoon picture. I don't think it's a fair representation, but anyway, just give you some idea of what this is. Okay, let me stop here. I have exceeded time by 10 minutes almost. I'm sorry about that. Yeah, so tomorrow we'll just prove this last property, and then I'll just wrap things up. Okay. Questions?